con el nuevo sistema ya no es necesario. Bueno, hola a todos, buen día. Es un placer para mí presentar al doctor Elías Fernández Santoro, que es originario de Argentina, pero vivió muy poco tiempo ahí y ha pasado gran parte de su vida en los Países Bajos o en Holanda. Completó su licenciatura en Ingeniería Aeroespacial y su maestría en Ingeniería Biomédica en la Universidad Tecnológica de Delft, donde se especializó en biomecatrónica. Como parte de su formación, realizó una pasantía en la Universidad Ben Gurion de Beersaba, en Israel, donde trabajó en la adaptación motora, hacia una tesis de maestría en neurociencia computacional, en colaboración con el Departamento de Neurociencia del Centro Médico Erasmus de Rotterdam. Tras finalizar su maestría, Elías asumió el cargo de coordinador en el Laboratorio de Control Neuromuscular en la Universidad de Delft, donde también trabajó como asistente de docencia y contribuyó en el diseño de sistemas dinámicos en neurociencia y modelado computacional, pues como lo indica su trayectoria, bueno, refleja una buena formación en ingeniería neural y neurociencia computacional, que es un campo que está todavía en desarrollo y con gran potencial acá, bueno, en el mundo y particularmente acá en México. Y bueno, realizó su doctorado en el Departamento de Neurociencia del Erasmus Medical Center bajo la supervisión de Mario Negrello y Chris Dessau, en el marco del proyecto de Arboio del European Human Brain Project. Su investigación se centra en el cerebelo y hoy nos compartirá los hallazgos más relevantes de su trabajo. En esta ocasión nos hablará sobre el control bidireccional en el sistema olivocerebeloso, y aunque bueno, entiende perfectamente español y pueden hacerle preguntas en español sin problema a los estudiantes, prefiere dar su charla en inglés porque bueno, ha vivido toda su vida en Europa y demás. Muchas gracias Elías por estar acá.
¿Me pueden escuchar? Hola. Buenos días. Bueno, gracias Román. Sí, bueno, primero un honor estar acá. Me pueden hacer todas las preguntas en español, por supuesto. Una de las razones que lo estoy haciendo en inglés también es porque hay gente conectada desde Europa y Estados Unidos viendo esta charla. Entonces, prefiero hacerla en inglés para que todo el mundo pueda entender y que quede ya registrado. Entonces, bueno, ya cambio al inglés, cambio de chip. So thank you for coming. It's truly an honor to be here at this university today. As Roman said, I just finished my PhD and I worked on models of the cerebellum, the olivocerebellar system. And I would like to discuss a little bit the work I've done these past years in this presentation. So first, let's discuss a bit about the cerebellum. I've been told by Roman and Lucas that there's not that much people working on the cerebellum here. So I'd like to introduce it with this video. Let's see if it works. So this is Serena Williams. She's going to serve. And when you see to serve, she has to track the trajectory of the ball. And she has to hit the ball with the racket and in the direction that she wants. And then if you see, even immediately, she positions herself to receive the ball back. So how is it that she's able to hit the ball with the racket? She's combining all kinds of visual and position inputs to continuously adapt her movements. The underlying mechanism in the brain to be able to do this has two important brain structures. The first one is the cerebrum, which contains, amongst other things, the primary motor cortex, and the cerebellum, on which I will focus this presentation. The cerebellum, the olivocerebellar system, is a part of the brain. Here it's located on top of the pons, and it facilitates learning and controlling movements. To coordinate these movements, it integrates the sensory motor information with motor command signals and is able to continuously adjust during motor learning and resulting behavior. And there is a continuous exchange between the cerebellum and the cerebrum. Now, I tell you that this is important for motor command and coordination, precision of movements. What happens when we have a disease or an injury to cerebellum? You get what we call ataxia. I would like to show you one part of this video, if I can. Is this experiment where the patient with the cerebellar disease tries to point towards his nose and then the finger, and then later on they will move the finger, and it will be very hard for him to coordinate the movement and have the precision, and most of it will be also based on on his eyesight, so it is not as automatic as it should be. You can also have difficulty swallowing, difficulty walking, tremor. All these things happen because there's disease in the cerebellum. So another thing to keep in mind is that with the invasive techniques that we use to be able to get to the results from the cells or from the neurons, we cannot perform these experiments on humans. So we use mice models. And we found that a lot of the results from the mice we can extrapolate for human results. And as I know that most of you work in different parts of the brain, I wanted to take a little minute to contextualize and see where the cerebellum fits inside the brain. So if we start from the primary motor and sensory cortex, the M1, S1, they give input to the thalamus, the MDJ, the mesodencephalic junction, and the pontine nucleus. The MDJ is a giant hub that integrates motor and sensory input and gives input to the cerebellum through the inferior olivary cells. From the pontine nucleus, the mossy fibers rise to the cerebellum and they give sensory motor information to the cerebellum. And then the output of the cerebellum, which is through cerebral nuclei, which I will show you in the next slides, they go to the thalamus, which also feed back to M1 and S1, and then together the output of the cerebellum with M1 and S1 go down for motor control. So if we zoom into the olivocerebellar loop, which would be the cerebellum with the cerebral nuclei and the inferior olive, they form the olivocerebellar loop. And this one consists of the cerebral cortex, shown here. The main cell of the cortex is the Purkinje cell. These cells receive all the incoming sensory and motor information. They transform it and they generate the entire output of the cortex. The sensory motor information is received from the Pavlov fibers, which are received from the excitatory mossy fibers. And the cortex is also made up of various molecular layer interneurons, which are there, but we don't discuss it further in this work. The output of the cortex, as I told you, the Purkinje cell generates it. It goes through the Purkinje cell axon to the cerebral nuclei, and the cerebral nuclei inhibits the inferior olive, and the inferior olive feeds back into the cortex via the climbing fiber. So if we zoom in, and I'll repeat again exactly this loop because I will then discuss how I model it. Summarizing this, we have the main neuron, the Purkinje cell, which inhibits the cerebral nuclei. Cerebral nuclei is the only output of the cerebellum. Some of these cells also inhibit the inferior olive. The sensory motor information comes from massive fibers through the Pavlov fibers into the Purkinje cell. And these Pavlov fibers, there are over 200,000 connecting the Purkinje cells. They're excitatory and they can modulate the activity of the Purkinje cells, these spikings that we call the simple spikes. An individual Pavlov fiber, they form relatively weak synaptic connections with the Purkinje cell, but as a group, they can really modulate the Purkinje cell and even double its intrinsic firing frequency during sensory motor control. The input of the inferior olive is given through the excitatory climbing fiber pathway. In most mammals, each Purkinje cell receives from a single climbing fiber from the inferior olive. And this climbing fiber delivers a very powerful excitatory input, which results in an all or nothing complex spike. The complex spike is very different from the simple spike, which is the intrinsic firing rate of the Purkinje cell as well, which is between 50 to 100 hertz. The complex spike occurs at quite a relatively low firing frequency, which is about 1 hertz during spontaneous activity. The complex spikes are triggered mostly by the inferior olive activity. So they reflect the integration of all the inputs that go into the inferior olive. And it is interesting to note that the nuclei that also form the sources of the excitatory input onto the inferior olive also overlap with the sources of the mossy fibers. So the inferior olive also has sensory motor information. And during learning, we found that the Pavlov fiber to Purkinje cell synapse undergoes activity-dependent changes, and these changes are guided by the climbing fiber signals. So throughout this project, we concentrated on the plasticity at this synapse. And I wanted to explain a little bit, in big terms, the plasticity that happens. So at the synapse, you require to have a complementary mechanism that keeps this synapse in balance, right? So you have some depression, some potentiation of the synapse. If we look at the connection between the parallel fiber, the Purkinje cell, and the climbing fiber, if the input of the parallel fiber and the climbing fibers are activated out of phase, then you will have long-term potentiation. So the activity of the synapse will be increased. And if they are in the same period, the parallel fibers and the climbing fibers, then the synapse will be depressed. And you will have the process referred to as long-term depression. So ultimately, the direction of change, if it will be potentiated or depressed, really has to do with the moment, the timing of this climbing fiber input. So questions, of course, remain about how the stability at this synapse can be achieved in the olivocerebellar loop. And this is even more interesting when we look at different modules of the cerebellum because they have profound differences among them. So it was found in our department and in other works as well that there are zebrin-like zones in the cerebellum that have Purkinje cells that express an enzyme called adolase C and Purkinje cells that do not express them. In this work, always the Purkinje cells or the results in blue are the ones that express this enzyme, and in red are the ones that do not express it. And if we look at what we call a microzone, which is the cerebral cortex for the different zones, we find that actually there are different spontaneous intrinsic spiking frequencies that are different. So in the upbound, as we call it, which are the ones that do express the enzyme, you have a lower firing frequency address, spontaneous firing frequency, and you have a relatively higher frequency in the downbound zones, which are the ones that do not express this enzyme. Apart from the different spiking properties, in these different zones, there is also different topographic connections of the cerebellum. So when we add, let's say, the cerebellar nuclei, and we have this, what we call the microcomplex, we also see that there's different behaviors of the cerebellar nuclei. And then when we add the inferior olive and we have the olivocerebellar loop, also called a micromodule, and I use this during the presentation, I switch between the two. We find that at the level of the inferior olive or the complex spikes, we also have that in the upbound, the firing frequency of the complex spikes is lower and the one of the downbound is higher. So apart from these different intrinsic firing frequencies, we also have found that there's different propensities for the induction of plasticity in these different zones. So by that, I mean that some zones have a propensity for potentiation and some zones have propensity for depression. And these have been also, during some experiments, have been associated with specific learning tasks, and these tasks require either an upbound or a downbound change, so potentiation or depression. This has been found through various experiments, and I would like to show you one of them, which is an experiment that we use a lot in cerebellar conditioning. So it is purely cerebellar because it doesn't involve presence of cognition, and it's what we call eye blink conditioning. So you have two types of conditions of stimulus. You have the conditioned stimulus, which in this case is the tone, and the unconditioned stimulus, which is the air puff, which generates the unconditioned response, which would be the eyelid closure. So before learning to the mouse, you give the puff. As a response, the mouse closes the eye because, of course, it's a lot of input. But if you just give the sound, the tone, nothing happens. Then during learning, you first start with the sound for some time, and then you get the puff, and the mouse closes its eye. And after repetitive blocks of learning throughout a few days, you end up with conditioned learning where if you only give the sound, then after the time where the unconditioned stimulus should have happened, the mouse will close its eye because it learned that it will come. And after doing these experiments, we found in our department that already maintaining this difference in simple spike activity, spontaneous activity, the different zones had different propensities so for learning, so for adaptation of the synaptic weight. So you have in the upbound zone, the activity goes up, so the activity of the the firing frequency of the Purkinje cell goes up, and in the downbound zone, it goes down. So before we move on, I would like to do a small recap of the cerebellum. So it's involved in coordination, precision of movements. The main cell is the Purkinje cell. It integrates sensory motor input, and it gives the output of the cerebral cortex. The plasticity that we looked at is at the parallel fiber to Purkinje cell synapse. And we have different micromodules, the upbound and downbound micromodules, which have a different intrinsic activity of those Purkinje cells and have different propensities for learning. So the motivation of our work is we wanted to understand if between these different micromodules are there common mechanisms to stabilize these changes in synaptic weights. Why is that? Because our hypothesis is that the changes in weights are what underlie the learning process. And we also thought that, okay, the resonant dynamics of the loop are key to stabilize these synaptic weights during procedural learning in both micromodules, up-down and downbound modules. There was a challenge, of course, is we have no idea, and we need to elucidate the factors that determine the exact timing and precision of this learning. And to be able to do this, and to test this hypothesis, what we did is we generated a novel network model that represents different modules with different intrinsic and electrophysiological properties of the Purkinje cell. So, as I told you, our hypothesis is that the parallel fiber to Purkinje cell synaptic weights are stabilized during learning. And this is done due to the resonant dynamics of the model. So the model that we developed is one that is decoupled from the rest of the brain, and so that we can really focus on the resonant dynamics of this loop. So we start with 5 parallel fiber bundles. I told you we have over 200,000 parallel fibers. Well, we can bundle them because they come from similar sources. And you can think of these parallel fibers as thousands of parallel fibers together. They go into the 100 Purkinje cells, which inhibit the 40 cerebral nuclei, which will also inhibit the 40 inferior olivary cells. These inferior olivary cells, they're able to oscillate, so they have subthreshold oscillation, and they have gap junctions. But I will discuss this further. So the input we gave is a stochastic input that represents all possible inputs that go through the bundles. This is how it looks like for the five bundles. Then you multiply them by the different synaptic weights. Each Purkinje cell has 5 weights. You have 100 Purkinje cells, so you'll have 500 weights. You can think of these weights as meta-synaptic weights because they represent the average change of the thousands of synaptic weights inside the bundle. Then each bundle current times the weight summed together gives you what the soma will see, which we call the postsynaptic current. And this is what will drive the activity of the Purkinje cell. Then the Purkinje cell and the cerebral nuclei, we use the same type of model, which is called an adaptive exponential integrate and fire model. It is simple enough that we can do all sorts of simulations without being computationally expensive, but it can still give us the behavior that we want. So the Purkinje cell receives the postsynaptic current. Here you can see how it responds. You have the membrane potential on top and then the rasters. And we tuned this Purkinje cell. So what I mean by tune is we chose the different parameters for the model so that it could reproduce the different activities that we see in upbound and downbound. So this is important because later on in the results, it will become a bit confusing. What are the things that I fixed at the beginning? What it is that is just the model doing its thing, so it's important that we keep in mind that this is really what I tuned. I chose the parameters specifically to be able to reproduce these things for the Purkinje cells. For the cerebral nuclei, we can see is also already how the behavior affected. I told you that the Purkinje cell inhibits the cerebral nuclei. So you see that when there is a pause, so when it is not inhibiting, you get more spiking of the cerebral nuclei. But then when there's more firing of the Purkinje cells, you see less spiking of the cerebral nuclei. This I will discuss a bit further in the presentation. Then for the inferior olive, I think I will take some time to discuss it because it's actually, it has rather unique properties. You can see here in this video, which is a simulation that my supervisor, Mario Negrello, made, and where you can see the different clusters, because the inferior olive is probably one of the most densely coupled electrotonically cells than any other type of neuron in the mammalian brain. And you can really see how they affect each other. So I chose a 3-compartmental model that is based on a model from Schweighofer in 1999. Here you can see 2 compartments. So in modeling, when we discuss compartments, we're really saying, okay, a part. So the soma can be a compartment. The axon is a compartment. You can have a general dendritic compartment, but you could have cells with a lot of the subparts of all the dendrites are also different compartments. So we started with the Schweighofer model, which is 2-compartmental, dendritic and soma. Then we used the De Grauw model, which expanded it with the axon. So the driving equations are just these differential equations. This is, for example, the memory potential of the soma. And you see that you have all the ionic channels in the soma. Then you have the leak of the soma, and here is the exchange between the different compartments. The DS is between the dendrite and the soma, AS between the axon and the soma. Then here's the membrane potential of the axon and the one of the dendrites. Now, what's important with this model is the coupling, so the gap junction between the neurons. You can see at the dendritic level, so this IC. So what does this mean? It means that if we turn it on, the cells will drive each other. So the activity of one cell will affect the other, and this is how it responds for a certain input. These are 40 cells. Now, if I take the exact 40 cells with the same input, same parameters and everything, but the only thing I say is this coupling is equal to 0, then you get this result. So you end up with more variability in the firing and actually less firing rate. So it really drives the firing, the synchronicity, but also the firing rate, this coupling. And the other aspect that I told you about is that these cells are able to oscillate. So we have this current, this IH, which also drives the subthreshold oscillation. For our model, we have a subthreshold oscillation of about 4 to 6 hertz. And the way we tuned it also is try to reproduce the data that was found by Haibo Zhao in our department in 2014. Similarly to the Purkinje cell, we have a difference between the different micromodules. And again, these parameters are the ones that I chose so that we could reproduce these firing rates. Then how does this look if we put it below the
de la oscilación, pero por la variabilidad que encontraste en los dos módulos.
Es una combinación. Con el H puedes poner la amplitud y la frecuencia, pero por supuesto cuando vas cambiando otros parámetros, afecta también esto. Entonces terminas que en los dos módulos es entre 4 y 6 Hz la oscilación, la amplitud es más o menos la misma, pero también va cambiando con la frecuencia del spiking. Okay? Yes, so when we put them all under each other, you can already start to see the relationship between all these cells, right? So I told you already, when you have more firing of the Purkinje cells, you get less firing of the cerebral nuclei. But actually, you can also see that when there is firing of the inferior olive, you get a pause at the level of the Purkinje cell, which then results in disinhibition and more firing of the cerebral nuclei. So let's look closer at the connectivity. A Purkinje cell is inhibitory to the cerebral nuclei. How did we model this? I said for each simple spike, you have a negative current that enters the cerebral nuclei. And then from the cerebral nuclei to inferior olive, it's also inhibitory. We modeled a differential equation that can really represent the activation time of the inhibition, the GABAergic inhibition to the inferior olive. And from the inferior olive to the Purkinje cell, we actually modeled it as an inhibitory signal. But if you remember at the beginning, I told you the climbing fiber gives a huge excitatory input to the Purkinje cell. And then what happens is you get this huge influx of calcium, you get your complex spike, and then there is a pause due to the hyperpolarization. The way we did this is we said, okay, the IO spike is a complex spike. And then after that, we modeled the pause at the Purkinje cell, also to respecting biophysically accurate results. Then If we look closer to where we actually modeled the plasticity, which is at the Palo fiber bundle to Purkinje cell synapse, the plasticity is represented by synaptic weights. So the weight that the Palo fiber bundle is multiplied by this weight, you sum them all, and you get the postsynaptic current. And when plasticity will be turned on, the synaptic weight will be updated by two mechanisms. One is a homeostatic mechanism that is based on the Bienenstock-Cooper-Monroe plasticity mechanism. And the second one is just depression due to complex spike activity. So we start with the homeostatic mechanism. You can think of it as encapsulating both the long-term potentiation and the intrinsic homeostatic mechanism that the Purkinje cell has, which has been shown also in experiments. The changes in weight, dWi/dt, is driven by this equation, which depends on a general Purkinje cell change in weight, modulated for each synapse with the instantaneous activity of the Palo fibers. The tan H that we put there is my addition to this mechanism, which allowed us to set the only limit that we put in the whole model. We said you cannot have firing above, like you cannot have potentiation above 250 hertz. So we say that Purkinje cells that fire at 250 hertz, they enter pathological levels. So you can only have depression. And it's the only guiding and hard rule that we put in our plasticity mechanism. So in this, what's interesting and what makes this homeostatic mechanism is this threshold, this theta, as we call it, which depends on the activity of the Purkinje cell. So what does this mean? It means that if the Purkinje cell activity goes up, then theta will go up and you have more chances of having depression. And if the activity of the Purkinje cell goes down, theta will go down and you have more chances of getting potentiation. So you always stay continuously adjusting the weights and the frequency of the Purkinje cell. Here's a small video I made of how this looks like. On top, you have the theta, how it moves, and you see the function, how it changes. And at the bottom, you see with the blue line, which is the one that is quite bounded between 100 and 130 hertz, which is the activity of the Purkinje cell. So you can really see that theta changes really fast and quite a bit, but it helps to maintain the activity of the Purkinje cell where we want. Now, for the second component, which is the depression due to a complex spike, it's quite simple. You get a negative change in weight, which is proportional also to the instantaneous activity of the Palo fiber. So you have difference for each of the synapses. And for the time for it to decay is about 1/3 of the firing frequency of the nuclear olive, about 400 milliseconds, which can be thought of as the time it takes for the calcium to leave the cell. So when you have an IO spike, you have a depression, a negative change in weight, which is proportional to the activity of the Palo fiber. And then when we add also then the change in the homeostatic mechanism, you can see that after an IO spike, which generates a pause, so it lowers the frequency of the Purkinje cell, you get a potentiation of the weight because it wants to increase the activity of the Purkinje cell. And then when you sum them together, you get this green line, which is the D change of the synaptic weight. And you can really see that even though the depression seems to be quite high, at the end, the changes in weight for a 10-second experiment or even a 100-second experiment can be 10, 12%. So it's not too drastic. So what did we do with this model to test our different hypotheses? We did some simulations, and I want to explain to them. So first, I want to explain the concept of what I call plasticity epoch. It depends first on the no plasticity simulation, where the synaptic weights, we've generated them randomly, and they sum to 1. So you can have already all the inputs distributed at the Purkinje cell level. These weights don't change during the experiment. We give the current input, the Palo fiber bundle input, which we've run also externally, so it's a frozen input. And then we see how the cell responds. Then we have the plasticity experiment, which is when we turn on the plasticity mechanism, so the synapses, the weights can change, and we give the same input again. And at the end of this experiment, we take the last second of the weights, an average of it, and we say this is the new static weight, and we do the same experiment with the same input again. This will allow us to compare how the model has changed and adapted to this type of input. Then, of course, we have with coupling and without coupling for both modules, all of this. And we have an experiment with filtered inputs, which I will discuss a bit later. So another recap about the model. We have a model that has Purkinje cell, cerebral nuclei that are adaptive exponentially integrated Fire models. The Purkinje cell is subjected to stochastic inputs. We have an IO that has coupling and has two compartments. Our plasticity mechanism is at the parallel fiber to Purkinje cell synapse. And it has homeostatic and long-term depression mechanisms. And we have two experiments for each module, one with coupled and uncoupled, and the other one with the filtered inputs. I want to take a second to tell you that when I discuss coupled and uncoupled, the experiment, the network is always the same. It's the same parameters, the same connectivities. Everything is the same. The only thing that we change is this coupling current. We make it 0. And when we talk about upbound and downbound, it's also the same. Same connectivity, same parameters, except the few parameters that drive the activity of the Purkinje cell and the inferior order. So everything else is controlled and it stays the same, which helps us to compare really the results. So I discussed in the introduction that we found bidirectional changes in the simple spike activity, and these are expressed in upbound and downbound micromodules, and we're actually able to reproduce them with our model. So again, our model is at the bottom, and these are the data, the recordings that were found. It's actually a sketch from this review from Chris Deseo, which represents the different results. Again, it's important that I stress that the only thing I did was I set the initial parameters for the firing frequency, and that's it. We just turn on plasticity, so there's no direction in our plasticity. The only bounded part is you cannot have potentiation after 250 hertz. And what happens when we turn on plasticity? We find that in the upbound, the ones that start with a lower firing frequency, it increases the activity during learning, and the same happens for downbound, but it decreases the activity. So these results, what they suggest is that because the only difference between the two upbound and downbound is just the intrinsic activity of the Purkinje cells at the beginning. So what it suggests really is that already the initial level of Purkinje cell activity is enough for this plasticity mechanism to establish the direction of plasticity. And I didn't show it here, but the direction of plasticity stays the same for whether or not you have a presence of gap junction. So it doesn't matter, you have the direction. Now, another hypothesis that we had was that the synaptic weights that change in one direction or the other, so they increase if you have potentiation or decrease when you have depression, they will reach a new level and just stay there. With the same input that you give it, at some point it would just find a new level and just stay there. So what we did is we did multiple of these plasticity epochs. It was static weight, plasticity, static weight again, plasticity, static weight, plasticity, static weight. And what we found is that already at the end of the first epoch, you have already the changes in the weights. You get potentiation, so the weights increase for the upbound and the weights decrease for the downbound. And then the subsequent plasticity epochs, there's not that much difference, a little bit, but it's mostly stable. And we can see this in these box plots where they show the difference in the weights of each synapse with the previous epoch of plasticity. And you can see really there that you get an increase of the weights for the upbound and a decrease for the downbound. And then for the rest, they're mostly at 0, the changes.
¿De esto hay alguna, de esta parte del anterior entiendo que los datos experimentales que hizo,
sí.
¿De esto hay alguna evidencia o alguien que haya dado que habilitan así la plasticidad?
Y que yo sepa, no, porque también esto de poder apagar la plasticidad en experimentos es casi imposible, no puedes parar la plasticidad. Entonces, sí, no es...
Pero no hay una estabilización.
Sí, se estabiliza, eso sí, pero en un experimento, por ejemplo, tenemos un colega, Stein, que hizo, pero eso es más in vitro, con las células hizo induction de plasticity y mostró esto, mostró que en la upbound sube la actividad y en la downbound baja, pero son induction así chiquitos durante un poco de tiempo, porque las células se mueren, y entonces se estabiliza, pero está hablando de media hora. Pero así con todas las neuronas, toda la población, no, que yo sepa, no.
Y en las enfermedades no sabemos si eso es lo que está fallando o qué es.
No. No creo. No, porque pueden ser las conexiones más que. Entonces no sé si es la plasticidad o las conexiones que te activan la plasticidad, ¿no? Entonces, no sé qué viene primero. Sí. So, another hypothesis that we had was that there would be specific characteristics of the input that would elicit these complex spikes. Why do we care about the complex spikes? Because again, the complex spikes is what drives the direction of the change in the synaptic weights. So if we look at the postsynaptic current, again, the postsynaptic current is the 5 parallel fiber inputs times their weights summed together. So this is really the input that the Purkinje cell sees. So of course, after plasticity, those weights have changed. So the input that the Purkinje cell sees is different than before plasticity. But if we look before plasticity, what we found is that there are these oscillations or specific phases and frequency of about 5 to 6 hertz that increase and then decrease that elicit a complex spike. But if we say that the current increases, that means the activity of the Purkinje cell will increase and it will inhibit more the cerebral nuclei. So it will decrease the activity of the cerebral nuclei. But then it's followed by a decrease. So then it will disinhibit the cerebral nuclei, which of course will then burst or start firing more. So this at least two cycles of increase and decrease elicit complex spikes. And this actually was shown empirically by Lawrence Witter in 2 papers, 2010 and 2013, that I know of. And what we also found is that this decrease in the activity, so the disinhibition of the cerebral nuclei, overlaps with the bottom of the subthreshold oscillation. Now you see there is a synaptic delay of 60 milliseconds. This is something that we set based on experimental results, which is more or less a 10 millisecond delay between the Purkinje cell to the cerebral nuclei and 50 millisecond delay between the cerebral nuclei to the IO for the time that it takes to start the inhibition. And then if we look further, how does this look after plasticity? We find that it's very similar, but that the amplitude in upbound has increased and the amplitude in downbound has decreased, which this just validates, or is just another way to see the changes in weights, because the weights have increased, so you see more of the current. So of course, if you sum it together, you see more of the postsynaptic current and the other around for the downbound zone. So the previous hypothesis was that specific characteristics of the input would affect complex spike generation. We expanded this hypothesis to the whole loop, and we said, okay, the different frequencies in the input can differentially influence the dynamics, the resonant dynamics of the whole olivocerebellar loop. So what we did is this experiment. We took, again, for all these experiments, is the same network with all the same parameters and the same input, which is this no filter input, is just the original parallel fiber input. But then in the next experiments, what we did is we added a step in between and we filtered this input. So it's also something that we can compare. Why did we do this? Is because we know that signals from different sensory motor sources, they have different spectral properties. And also Purkinje cell populations, it's been shown that their activity contain different frequency bands. The different filtered signals, we normalize them to keep with the same spectral power. And also, which I don't show here, is we found that the cerebral nuclei dynamics for each of these inputs doesn't change almost at all. And this really shows that there's a high level of divergence of the signal and mixing of the cerebral nuclei. But then if it's more interesting to look at the Purkinje cell activity, so the simple spike frequency and the complex spike frequency, what we can really see is that the different frequencies can change the sensitivity of the loop, especially if you look at very low frequencies. You see here, you see that the inferior olivary cells, the activity goes up. But if you look for the higher frequencies, it's quite robust. So it also shows that you can have the network of the Purkinje cell that is robust to frequency variations, because the mean more or less is the same throughout the experiment. Then we tried to understand a little bit more why we had this result. So we looked at yeah, the relationship between the spike frequency of the inferior olive, where we saw the most change, and the one of the subthreshold oscillation frequency. And what we found is that for both upbound and downbound, there is an inverse relationship between the subthreshold oscillation frequency and the inferior olive vary frequency. So you see that we have an STO frequency of between 5.8 and 6.2 hertz in the IO frequency, and you really see this inverse relationship. And this is interesting because thinking about the gap junction level, if you remember this figure, when you take away the gap junction, you're also changing the synchrony, and you're changing the frequency of the spikes, of the IO spikes. So then we said, okay, how does this look for the uncoupled scenario? And what we actually see is that the selectivity of the frequency here that we had seen, this very different response, completely disappears when the gap junction is removed. Yeah, so another recap, the third and final one. Yes. So we know that there are these intrinsic differences between the activity of Purkinje cells in the different modules. But what we were able to find is that putting them in the mechanism of the loop enhances these functional differences, and the plasticity mechanism with the homeostatic and the complex spike dependent LTP rules and LTD drive this to stability. We have a strong preference for specific frequencies and phases of the polar fiber input. The probability of the complex spike is modulated by specific temporal features of this input, which then disappears when the gap junction is removed. So what can we conclude from this model is that we found through the model that just the starting difference, so at the no plasticity, just the difference in starting frequency of the Purkinje cells, it drives the direction of learning, upbound or downbound. And this is in line with various ideas that exist, that different modules are associated with specific learning tasks that require either upbound or downbound changes in this simple spike activity of the Purkinje cell during training. Another thing we saw is that the response of the model is modulated by input frequencies. So this means that we can specifically choose, or we can choose a specific input that gets this model to respond more accurately to biology or to specific experiments that we want to reproduce. Also, we can think of brain-computer interface or other experiments that can benefit from trying different frequencies to get this type of outputs. And finally, we have the experiments I showed you is with high coupling and very low coupling, 0 really. But this actually, in reality, the amount of coupling is quite dynamic. I showed you the two extremes, but the coupling is also affected by the inhibition of the cerebral nuclei. So if we think about the whole loop again, we start with the parallel fiber input, which drives the Purkinje cell activity, which then in turn drives the inhibition and disinhibition of the cerebral nuclei, which then affects also the coupling of the inferior olive. And that changes the selectivity of the input. So there is an interplay between the coupling and the parallel fiber inputs. And this is in line with theories that say that the cerebellum has different modes of learning depending on the context. So the future work, what I think this model can now be used for is, well, first, I used parallel fiber input, just this stochastic input, and I compare it to behavioral experiments. Of course, one next step would be to actually simulate a behavioral experiment, the eye-blink conditioning. So we can just say the conditioned stimulus goes through one of the parallel fiber bundles, the unconditioned stimulus goes to another parallel fiber bundle, and it goes to the IO to elicit the complex spike. Another thing is to use a better PC model. Better is a strong word, but that has more mechanism, that has at least the calcium mechanism, so that really we can model the input of the clamping fiber through calcium input and really model the different lengths of the Purkinje cell pauses due to this. And finally, I showed you this connectivity at the beginning, and I showed you that there was this input from the MDJ to the inferior olive. And it has been shown that only in upbound modules, there is a feedback that goes from the output through the MDJ excitatory to the inferior olive. And this would be also interesting to see what does this mean computationally for this model, and if it changes even more the differences between upbound and downbound. And yeah, I would like to say thank you to the supervisors that I had during my PhD. So Chris Ezeu is the department chair, Mario, Alexandra, and Lawrence. Thank you for listening. This is the website if you want to have more information about our department, and my email. And since I have a little bit of time, I wanted to tell you a bit, but I think I can do it in Spanish, but I'll just do it in English. So Roman said that after my master's, before my PhD, I worked in Delft, and I wanted to show you a bit what just quickly the type of work that they did there. So it's really, they use these different robots. The first one is the arm movement and disturbance analysis. So it's a haptic manipulator. You can really change the strength of the device, and they investigate the interaction between shoulder, elbow, and wrist during maintenance and movement. We have this one, which actually I had to repair a couple of times when I worked there, is the Propio manipulator. And it's actually, I think it's one of a kind because it was built there. And it's operational since 1980. So it's very old. And yeah, it's another haptic manipulator. You really have to control the force that is coming, and we measure with the EMG your response. And then you have the gas pedal, which is really to investigate they want to investigate the possibilities, like the limitations of providing haptic feedback. So haptic feedback is really just the response to help you on the gas pedal to really see, okay, an obstacle happened or something, you can really feel it on the pedal. And this is this type of experiment. And yes, thank you for your attention.
Pensando un poco con la idea esta que tenés de multiplexar el contexto al cual tiene que abocar él. Entonces eso va un poco con la idea de utilizar distintas bandas de frecuencia para actualizar al cerebelo. ¿Es algo por el estilo?
Sí, podría ser. También podría ser, no sé, si querés usar este modelo para controlar, no sé, un brazo mecánico o algo, o decir, bueno, la frecuencia de activación de los músculos es 15 Hz. Entonces por ahí decir, bueno, ¿cómo respondería para eso? ¿Qué es lo que está pasando? Se puede pensar en muchos contextos, no solamente contextos de lo que está haciendo, pero también de la sensory motor information que estás recibiendo.
Es un poco la idea que tiene Busaki, bueno, para el hipocampo, pero utilizar distintas bandas para distintas zonas de delta para interactuar distinto con distintas áreas. Entonces eso, pues, o sea, en otras áreas cerebrales ya se ha mostrado como un mecanismo plausible para decir quién anda conectando. Pero bueno, no sé. ¿Preguntas? ¿Un estudiante quiere preguntar? Tengo una pregunta. Buenísima charla.
Gracias.
El esquema con el modelo existe bastante complejo, ¿no? Distintas capas, distintos tipos celulares, ¿no? Me preguntaba un poco si el término que vos introducís de plasticidad en las cuestiones diferenciales, ¿no? Estás un poco influenciado por las células granulares que no modelaste, que no incluiste en el modelo.
Sí.
No, digamos que generan un input muy fuerte a lo que es la estructura network cerebral.
Sí. ¿Tenés eso?
¿Qué pensás?
Tenés eso y también tenés los molecular layer interneurons, las basket cells, las stellate cells, que también lo que hacen es, de una manera participan al mecanismo homeostático de la Purkinje. Porque si vos activas las parallel fibers, te activa las molecular interneurons que son inhibitory a las Purkinje, entonces también te baja la frecuencia. Y con las granular cells también tenés activado ahí. Entonces también le agrega como una capa de complejidad y probablemente te muestre que la plasticidad, que es dependiente, por supuesto, de la actividad y todo eso, también es dependiente de otras cosas.
Esto.
Bueno, bien.
Bien, pues, bueno. suerte y ojalá tengamos de vuelta por acá.
Bueno, gracias por la invitación.